Come on in, everyone. We're a couple minutes early. Feel free to ask me questions while we wait. I got my picture up. Check it out. Cool, huh? More people coming in. Come on. Got 12 of you in here. Anybody have any questions before we get started? It's we got 2 minutes left. So feel free to ask away. Just living my best life, drinking coffee, sitting by my clothes hanger, i.e. exercise equipment. We got 15 of you folks in here. Good job. Like I said, feel free to ask aloud, just speak up if you have any questions. I'll try to keep an eye on the chat, but it turns out I'm evidently not very bright or attentive because I constantly have students saying, "Hey, somebody left you a question in the chat." So by all means, let me know if there's something in the chat that I haven't paid attention to, especially when I share my screen because I always forget to reopen the chat window. So if someone's asking something, you can feel free to just speak out if you post a chat and it never happens. You can do your raise the hand thing, but I really don't mind you interrupting me. If I see your hand raised and I'm in the middle of finishing a sentence or a thought, I might say, hold on a second, or I might just keep on going and then answer you. But I don't mind if you slow me down by, asking me a question while I'm in the middle of speaking, that's fine. If it becomes too much of a nuisance, I'll readjust it later and let everybody know. But right now it's perfectly fine for you just to speak up and say, hey, I have a question, or what did you get on that line or whatever. All right, so it's now time for class to begin. I now have 16 of you helpless souls in my class. I hope you all can survive. No, I'm just playing. Not only are you guys going to survive my class, you're all going to make A's. I'm confident. That sound good? All right, so it still looks like we have no questions, so I'll go ahead and jump into chapter 2. Chapter 2 of your textbook is basically on kinematics. So the study of physics has a lot of different branches. One thing is mechanics, and mechanics is how do you make things move and get them to reach certain velocities, certain accelerations, go certain distances in a particular point of time, or get to a certain place. So, imagine all the ways you might want to deal with a baseball. Okay. Mechanics answers that. It also happens to answer the statics question, which is what if you want to build a house? Okay. Or what if you want to build a baseball? Or what if you want to build a bat? All those sort of things. Those are also parts of mechanics. But then mechanics can be broken down into study of motion, which is kinematics, or if you're in health sciences, they call it kinesia, or they call something similar kinesiology. But basically, motion is kines, K-I-N-E-S. That's the origin of it. But when we study what we're doing this chapter is kinematics, that's a portion of mechanics, but it's specifically the portion of mechanics where you try to understand motion without necessarily understanding what caused it or what causes it to change. In other words, I can tell you that if an object's moving at an initial velocity of 1 meter per second to the east, and that its acceleration is 3 meters per second every second to the east, then I can tell you at any point in time later what its velocity will be and what its position will be, period. Okay, I don't need to know anything about how that happened. I just am given the information of at t equals 0, the initial velocity, the initial position, and the acceleration. And basically, as long as those things stay set, then I can predict where that object will be at any point in time later. And that's all kinematics. Now, if you tried to say, well, Mr. Younger, what made that thing accelerate at that rate? Then I'd have to go into the dynamics portion of mechanics. And the dynamics portion of mechanics is really Newton's laws of motion. Newton's first law of motion: an object in motion tends to stay in that state of motion unless acted upon by a net external force. Newton's second law of motion: the acceleration an object get is directly proportional to the total force acting on it and inversely proportional to the mass or the inertia of that object, and the acceleration points in the direction of the net external force. That's the second law. And then Newton's third law: for every action, there's equal but opposite reaction, which basically says if A pushes on B with a force of F, then B pushes back on A with a force of negative F. Okay, so those are three laws of mechanics that Newton came up with. And he said, if I have seen further than others, only because I stood on the shoulders of giants, which is a very humble statement, which if anybody knows anything about Newton, he is the antithesis of humble. Okay, so that was kind of humble, and it goes down in history as this great humble statement, but he actually did it in front of the Royal Society. Sadly, the same group that has been really, really famous up until lately, and now Elon Musk is one of them. So I'm really sad about the Royal Society, mainly because Elon Musk has kind of made me quite aggravated with some of his really stupid statements. The fact that he's a fellow of the Royal Society is just. But anyways, go back to that. At least he's making kick butt, electric cars. So the Royal Society at the time of Newton was initially being run by a man by the name of Robert Hooke. And Robert Hooke was one of Newton's many personal enemies. And he was in the audience when he said that. And in fact, what he's saying is, if I have seen further than others, and use the U, by the way, when it's a metaphoric distance, and the A and farther when it's a real distance or something like that. So if I have seen further than others, it's only because I stood on the shoulders of giants. Is also saying, if I've seen further than others, it's only because I stood on the shoulders of giants, not scrubby little stinky hobbits like you, Mr. Hook. So you can think of it that way. So it was sort of a stab in the gut to Hook. Hook on many occasions blamed Newton for stealing his stuff, and Newton was essentially a hermit. He didn't go out anywhere. It'd be really hard for Newton to go out and steal anybody's stuff. He one time stared at the sun so long he got a migraine, and it forced him to stay in the house for weeks until the migraine went away. Thank you, Angela. Or Angelina, thank you. I got you. So anyways, that's just a backstory about Newton. We'll tell more of that later. I like to dice a little history in there because sometimes it keeps your attention. Sometimes it's crude or something like that. And that always catches people's attention, gets them to remember stuff. If you want to learn more about that, James Glick, Glick, wrote a good biography of Newton that's really thin. It's literally about that thick, but it's a really good, entertaining biography of Isaac Newton. And it talks about Robert Hooke in there as well. So anyways, that's what we're studying now is kinematics. And the first thing we need to realize is that in order to define a velocity, we really have to define a reference frame. So for instance, if I'm sitting here in my house and I'm looking over at the road and I see a bike riding by that way, to me, that's my negative x-axis. Normally I would say to my right is my positive x-axis. So I might give that bike a velocity, and if I could actually measure it, and I could, because I could take a little video, and I could measure the distance they traveled from one dot to another dot. In other words, literally put a dot in the photo and put a dot in the video and put another dot in the video, and measure the time, record the time at which the first dot was put, record the time at which the second dot was put, and that would be how much time passed. And then if I could measure the distance between the first dot and the second dot, that would be the distance traveled. And if I look at my speedometer of my car, it says miles per hour. And I know that's a speedometer, so I suspect it measures speed. And in fact, speed seems to be distance divided by time. So why does Mr. Younger need to give you another formula for speed? He doesn't. It's distance divided by time. And in fact, that's what we call the average speed. So assuming the person riding by on the bike wasn't moving very fast, it shouldn't be moving very fast, but was it changing their motion very rapidly? In other words, If you looked at them and from the first dot to say a third of the way to the second dot, they covered a really big distance. And then from the second dot to the third dot, from that second dot thing that I just put there to maybe halfway to the second dot, if they only moved this far, then that was a huge difference. You move this far in one interval and this far in another interval. That's a rapid change of speed within there. But if it looked like, they went the first 10th of the way in about a 10th of the time, the second 10th of the way at about a 10th of the time, and the third 10th of the way at about a 10th of the time, and so on and so forth, that would mean it looks like that's fairly uniform motion. Okay. So the average would be a great representative of that. But if it looked like in the first 10th of the time interval, say the time interval was, let's say 10 whole seconds. If it looked like in going from 0 to 10 seconds, they covered a distance like this big, but then in 1 second to 2 seconds, they covered this much. And then 1 second or 2 seconds to 3 seconds, they covered this much. That would suggest that the velocity is changing really rapidly, and the time interval over which I chose to measure the distance divided by time is not necessarily going to give me a good feel for how fast the bike was going. Okay. Does that make sense to everyone? Talking in the abstract here, or hopefully that's talking in the at least the metaphorical that's not abstract. I mean, I think you can all picture bikes riding by. So the big thing is if we can do that, we have some sense of the motion. But notice I said, according to me, she's going to the left, and that's my negative x-axis. Now, my neighbor across the street would be looking out like this and saying, oh, look at that bike going to the right. He's likely to call that the positive x direction, just because, most of us pick the positive x direction being to the right. So that's a whole different coordinate system, but the laws of physics should be the same in both of them, according to Einstein, which ultimately that's what he did with special relativity. But it was also the case with Galileo, only Einstein did some weird stuff to make it special. So yeah, it makes sense that the reference frame matters. In that case, just my neighbor versus me, it's just a matter of what they consider a positive direction, I consider a negative direction. So that's the only big change. They would still measure the same magnitude of the speed, for instance, or excuse me, they still measure the same speed, for instance, if they looked out and did that 10-second interval and then measured the distance from that first dot to the second dot. They divided that distance by the time. They would get the average speed over that 10-second interval. And if that speed didn't change rapidly in that 10-second interval, like I explained earlier, then they would come up with the exact same results like I did. Okay. So that's one thing, is you got to have everything measured with respect to a reference frame. I mean, you can in principle work without coordinate systems. There's vector mathematics you can use without forcing yourself to go into a coordinate system, but it's very rarely that you get to do that kind of stuff. Okay. Most often you have to just, sit down, piece of paper and pen, make a coordinate system, or take a video and make a coordinate system in that, as you'll see in our motion detector lab later. So that's one issue. Now, that's a simple case. That's a simple case of two relative frames just disagreeing on which way the positive x direction was. Notice they would have found, they would have said up is positive, and I would have said up is positive. So at least our y motion would be exactly the same, but our x motion would just be differing by a sign. So I would call the velocity positive, negative. They would call the velocity negative. Now, notice I just flipped into using the word velocity as opposed to speed. So that's a fundamental idea. And I'm sort of explaining this to you without so many notes because I really want you to understand this from the reading, but I'm trying to give you the concepts right now. Hopefully you've already read the material. That's truly the best way to prepare for or to take any class, is try to read the material that you're going to cover before you cover it, then cover it, take notes, ask questions, and then read it again. Again, maybe possibly taking notes, making more sense as the time goes on. That's the best way to study. But still, if you already read the book, you probably know there's some concepts like speed and distance and reference frames and all that. If you don't, that's okay. I'm sort of just giving you a rough idea of what that's about, so that it'll make more sense when you do read the book. Okay. So we've got reference frame here that we've already talked about. X-axis being to my right and x-axis being to their right makes for a opposite in signs of the velocity, but I'm using velocity and then I'm using the word speed. The definition I gave to you of speed specifically average speed, is exactly correct. So again, you don't need that. You don't need to make a new formula for this new concept of speed. You already know what speed is because you've been riding around in cars and bikes forever, and you've always, or for a long time, you've been dealing with things called speedometers. So a speedometer, again, has units of miles per hour per meters divide. So obviously, speed is a distance divided by time. And in fact, if you talk about average speed, you're just taking the distance traveled, measured in SI units would be meters, and divided by the time taken, which in SI units is seconds. So you get meters per second, okay? Now, if you did choose a time interval so large that it looked like what I said earlier was in that the first tenth of an interval, there was a huge difference from the second tenth of the interval from the third tenth, then you're probably, your average isn't that meaningful, so it's not that helpful. If you wanted to actually say, hey, I'd like to know what the speed is at any instant, then what you could do is you could shrink that down. Instead of doing that 10-second interval, maybe you go a 1-second interval and you take their initial and final spots. But if you divide that 1-second interval in space to the first tenth, second tenth, the third tenth, and so on and so forth, and it looks like there's quite a bit of variance there, then 1 second is not a small enough interval. Maybe you need to go to the 10th of a second. And you keep doing that until you finally find an area where it looks like throughout that whole time interval in space, it's always going about the same distance each time. Then your average for that has slowly been converted to your instantaneous speed. Now, what we were doing is taking the limit as this time got smaller and smaller, and we were dividing a change in x, delta x, divided by a change in time, delta t. The Greek letter delta being that triangle like that. That Greek letter delta in physics always means change in, and it always implies that you calculate the final value minus the initial value. That's what change in means in physics. Okay, so the change, or the speed, if you will be called delta x over delta t. That's the average speed. You would say that's equal to s, and you put a bar over it, or you could put it in those brackets like that. That's two ways of indicating average. So s with a bar over it is average speed, or s in those less than greater than brackets is an average speed. And that's just change in x, delta x, divided by change in time, delta t. But if you wanted to get the speed at any one instant, what you want to do is, like I said, take the limit of that quantity as delta t got smaller and smaller and smaller. And eventually you'll get to the point where delta x over delta t is the same thing. When you shrink the time interval smaller, it'll be the same thing you got last time, and then you shrink it smaller, it's still the same thing. Once you get to that point, your delta t is close enough to infinitesimal. That's the practical way of applying calculus. You know, in principle, calculus means you literally are supposed to shrink that down to, 0 point and then 999 billion 0 points and then a 1 or something like that. And that's still not enough. But in actually doing it, that's the way your calculator is going to do it, is it's going to find an interval that's small enough where it doesn't change from one interval to a smaller one to a smaller one. And then they'll say that's okay. So there's your instantaneous speed now. Okay. Now, the other part was speed versus velocity. And I will remind you that speed starts with the letter S, just like a word for a number. Does anybody know the word for a number that starts with S? If you read the book, you might have, or if you just know this, you might be familiar with it. You could also say it starts with a SC, if that helps you any.
Is it scalar?
Mm-hmm. Exactly. A scalar is a pure number, and that's what we're talking about here. So speed, which starts with S, just like scalar also starts with S, is a scalar quantity. So that's a nice little mnemonic for you to remember. The other part is also nice in that V, velocity, that's the symbol we use for velocity, is V. The average velocity would be something called the displacement divided by time taken. So it's still a delta x over delta t, but in this case, the delta x is a special quantity, just like the v is. So v for vector, and in fact, v for velocity, they both have the first letter v. So that helps you remember that velocity is a vector quantity. Or if you just watched Despicable Me, you would have known that the evil character in the first one was named Vector because he did evil with direction and magnitude. And that's actually a correct definition of velocity. So of vectors. Vectors are in some sense a quantity that has not only a magnitude, but it also has a direction associated with it. There's some other rules. It's actually the vector is actually a small part of a bigger thing called a tensor. But the main thing is it has a magnitude and direction for you guys. And right now we're not talking about vector fields and all that weird stuff. So as long as you don't screw up the direction or magnitude of the vector, you can move it around all you want. That's just fine. Later, you'll find out there's some problems with that, but that's the main thing. A vector is a quantity that has direction and magnitude. The only thing that you're sort of missing that might become relevant is that it actually has a very specific way of transforming, say, from one coordinate system to the other. So for instance, if I used my coordinate system, which had x pointing to the left, or excuse me, had negative x pointing to my left, there's a very distinct way to convert from that coordinate system to my neighbor's coordinate system, in which he thought that girl was going to the right in the positive direction. There's a very specific formula because it's a vector that tells you how to get from that coordinate to the new coordinate. That's the only deeper meaning that you need regarding vectors. Okay, so scalars just are just numbers without any kind of direction associated with them, and speed is a good example. Temperature is another example. Mass is another example. So there's several examples of things that are scalar quantities. I often treat pressure as an example, but you can actually define pressure in such a way that you get a vector as well. So I kind of stay away from that. Velocity, of course, is a vector quantity. There's also a quantity called displacement. And by displacement, I don't mean with respect to sinking bodies and stuff like that. There's a vector called the displacement vector that once you establish a coordinate system in whatever problem you're solving, you make a little X, Y, Z axis, say, where, well, I'll show it with my right hand, so it'll be right-handed. Okay, so this is my X axis, this is my Y axis, and this is my Z axis. And right here where all of them run into each other, that's the origin. Once you've done that, once you set up a direction that you're calling an X, a direction that you're calling positive Y, and a direction up that you're calling positive Z, and you locate an origin, then you can always define a vector that points from that origin to the point that you're talking about. Okay. When you say the displacement vector, what you mean is the vector that points from where you were, which was your coordinate origin, to where you are now. That's your displacement vector. So when we go to talk about average velocity, it's a little bit different than average speed. It's the displacement divided by the time taken, and displacement being a vector quantity. Now that makes it weird because displacement being a vector quantity, let's imagine a kid illegally somewhat touching home plate when he's up to bat in a baseball game, or she's up to bat in a baseball, softball game, whatever. Let's imagine that's that child's origin. Okay, so that's where they're starting, and that's when we're going to start looking at them. If you calculated their average velocity from home plate to first base, that would be fine. They're going to run, 50 feet or 90 feet, whatever league they're in. They're going to run some distance, and it's going to be some direction. Maybe that direction would be to the east. Okay, so you could say, okay, they ran 50 feet to the east, so the vector displacement is 50 feet due east. Period. That's you've now specified a vector. Yay, right? But if you actually go ahead and continue this and run around, you could say, okay, well, wait a second. The child went 50 feet, and they did so in 5 seconds. Then their velocity, their average velocity, would be 50 feet divided by 5 seconds, which would be 10 feet per second. Okay, that's really fast. It's actually as fast as gravity works in the first second. So most kids are not going to do that. We're talking about Usain Bolt here. Usain Bolt does beat gravity, or well, I should say, he beats gravity initially for like the first couple tenths of a second, and then gravity takes over. So that was not a reasonable velocity, the average velocity that I said for a kid going 50 feet in 5 seconds, but still the numbers worked out well. So that would be their average velocity, say from home plate to first. It'd be 50, or excuse me, it'd be 10 feet per second due east. Then they could say, what's the average velocity from home plate to second? Well, then it's going from home plate, and then you hang a left, and then you go another 50 feet, say, and they're actually at right angles to, well, actually, I guess you look at it that way. No, they're not at right angles. But what you do is you say, okay, well, my displacement vector now points from the home plate to second base. Okay, so you do that minus the zero vector, just means that new vector. And notice that vector has nothing to do with the 100 feet that the child ran. When the student or I keep saying student, sorry. When the child runs from due east from home plate to first, that 50 feet divided by 5 seconds gives me 10 feet per second as the average velocity. Then in running from first to second, they go like this. But the displacement vector is this guy right here, and that distance is not 50. It's not 100. It's somewhere between those. It's somewhere between 50 minus 50 and 50 plus 50, according to the triangle inequality. So now the direction is that angle, whatever that is, and the magnitude of that vector is the distance from home plate to second. And if you take that distance and divide it by, let's say, 10 seconds, then that would give you the average velocity. Now, if you keep on and go to third, it's going to be a displacement vector there. And then finally you get back to home, you see that the displacement vector is actually 0 when you get back to home. So the average velocity, no matter how fast Usain Bolt or any other kid ran from home plate all the way back to exactly to home plate, the average velocity would be 0. So that's the weird thing about average velocity, is it requires you to measure the displacement vector and then divide that by the time taken. And the displacement vector doesn't necessarily faithfully represent what you did, right? The displacement vector says you're a lazy bum. Yeah, you ran 200 feet, 50 plus 50 plus 50 plus 50. But you took, 20 seconds. If you're really awesome, you took 20 seconds to do it, and your displacement was 0. So it's acting like you're a lazy bum. That's what I mean by that. So any questions on that? All right, now that we've got this idea of speed and velocity as two different quantities, and average speed versus instantaneous speed as a limiting process, you can see that the limiting process applied to the velocity the same way would actually give you an instantaneous velocity. Again, it's going to be a delta x, which is a displacement vector, over delta t, but you're going to take the limit as delta t approaches 0 in the exact same way we did with speed. And in that case, you're never going to run into that weird 0 thing like we did with the average, because you're just not going to investigate a little area where you flip back and turn back on yourself. So we now have, in some sense, and I'll give you these equations in a few, even though they should be able to be pictured in your head now. We now have a sense of speed versus average speed versus instantaneous speed, and we've got a sense of velocity, what it is. It's a vector quantity with magnitude and direction. Average velocity, and then a instantaneous velocity. But the last thing we have to talk about with regards to these coordinate systems is, what if you see that little kid riding in front of my house, and they're going in my coordinate system in the negative x direction, and let's say they're moving at 10 miles per hour. That's a decent clip for a bike. Well, a person comes up behind them driving a car and is a little apprehensive because a kid riding a bike, they're just bound to fall over at any second or just jolt out in front of you. That could be a problem. So the car would probably be going quite slow. So you can imagine a bike moving at 10 miles per hour and then a car behind it moving at 5 miles per hour. Well, that car has a whole different coordinate system than me or my neighbor do. Now, that car might very well say, okay, I'm going to call straight ahead my y-axis. That's perfectly fine, because for some reason I said this axis doing this way was X, they could call that Y, or they could call it X, doesn't matter. The main thing is they would have an origin, which they'd probably say is maybe right where they are at the instant you start talking to them. And they would say their X-axis maybe points straight down the road in exactly the direction they're going. But because they're moving with respect to the road, and if you let the bike and the car ride for a whole hour and assume their motion is not going to change at all, the bike riding at 10 miles per hour relative to the earth and the car driving at 5 miles per hour relative to the earth, notice how I had to say relative to the earth, then after 1 hour, the coordinate origin for the car would have moved 5 miles, because that's what 5 miles per hour means. It means you move 5 miles every hour. In that same period of time, relative to the ground, the little girl would have moved basically from her spot to 10 miles. Okay. So for me and my neighbor, we would say, yes, she's clearly moving 10 miles per hour, and she did that for a whole hour. I would say her velocity was 10 miles per hour in the negative X direction. My neighbor would say her velocity was 10 miles per hour in the positive X direction. Now, here's the weird part, because in the car, the person moved 5 miles and the girl, and that was relative to the earth, and the girl moved 10 miles relative to the earth. That means the car and the girl are now only separated by 5 miles more than they were before. So in that car's reference frame, the girl is not traveling at 10 miles per hour. She's traveling at 5 miles per hour. So we've got to make up a frame with respect to that. And now's the time where I've got to basically give you some equations to make some sense of it. So does anybody have any questions on speed versus velocity, instantaneous speed versus average speed, instantaneous velocity versus average velocity, or vector versus scalar? Anything about that seem kind of confusing? All right, well, I'm going to go ahead and share screen now. Well, I say now, it's a long whole process, so we're going to do it either way. But the main thing is I'm going to share screen, and I'm going to try to remember to do my chat window, but by all means, speak out if someone's trying to ask a question. Okay, whoa, no, I did not mean to do that. I accidentally hit my camera. Okay, you saw my nasty desk. Right. So what we found here is a reference frame. So well, for starters, what I'm going to give you is some quantities. There's a quantity speed and average speed. You can write that like that, or you can write it like this. And it's just distance divided by time taken. Okay. Very typical result. Instantaneous speed. By the way, I can write this in symbol form as delta x over delta t. So instantaneous speed would be the same thing, but we're going to take the limit as delta t approaches 0 of delta x over delta t. Okay. And remember, this is a scalar, S-C-A-L-A-R. Then we introduce velocity. Which you put a little arrow over it like that to represent it as a vector. That's how we tell people, hey, this thing I just wrote down, that's not just your run-of-the-mill number there, dude. That is actually a vector, okay? And not only that, when you use that on a piece of paper and you put an equals next to it, it has to be set equal to a vector. So often, teachers in statics, dynamics, or physics, if you turn in something handed in and the left-hand side says V with an arrow over it and the right-hand side says 32 meters per second, they'll take off points immediately. Okay. It would have to say at least 32 meters per second, 15 degrees north of east or something. So just keep that in mind. But I'm going to say the average quantity, which can also be called like this, is actually equal to delta X over delta T. Okay. Now the big thing is X is the position vector. So if you imagine a coordinate system anywhere in space and you see a kid, you could say that kid is at position X by just drawing a vector from the origin to, let's say, the belly button of the child. Okay, because the belly button is pretty close to the center of mass. Maybe you have to go in an inch or two within the body to get the center of mass, but that's basically it. So the X is a position vector, but the delta X is the displacement vector. So for instance, let's imagine this scenario. Let's say this is your house. Okay. And you're going to start right here. So we're going to pretend like that's the origin. Okay. Then you're a little tired, so you wiggle and wobble down to the driveway. And you get up to the road and you stop. Okay, what that means is that's your X sub R. That is your position vector when you got to the road. Okay. Now, if you continue to walk across the street, actually, I shouldn't do that. We'll put across the street again. So there's the street, and I'll make it look streety. Okay. Now we're going to walk across the street. Okay, at friend's house. At t equal 20.0 seconds. Okay. So this one, oops. This would be, excuse me. This would be your displacement vector to your friend's house. Okay. And then maybe you and your friend walk to the store. You're awake now, so you're not straggling down the sidewalk quite so bad like you were before. And now you get to the store. Okay. Okay. Now you have another displacement vector. In this case, that is X store. Okay. Now, if you wanted your average velocity, you would have to take X store vector minus the zero vector, in other words, the origin, and you divide that by basically 10 minutes. So 10 minutes times, we're going to use the proper units. We're going to say 1 minute equals 60 seconds. And let's say this distance x sub s is equal to 500 meters. And that it points, I'll do it like this. That way I can call it a vector. We're going to get more into vectors. I'm just giving you a rough example so you have some idea what a vector is. We're all doing one dimensional this chapter, so don't worry, it's not time yet. But we're going to say this is at an angle of 30 degrees, let's say east of south. Okay. So your velocity would actually be 500 divided by 600, because 60 times 10 is 600. And that's zero. I don't even know why I looked that up. That's 0.833 meters per second. And it points in a, let's say a V. I'm going to do something special here. I'm going to write a little vector here and put a hat over it and just say that's a vector that's 1 unit long. So it has no units. It's not affecting the 0.833, but it happens to just point 30 degrees east of south. Okay. So that's how you compute average speed. You just take the final vector minus the initial vector, and that's your average. Okay, so that's what I was explaining before. If you wanted to do the average speed for that one, you would have to get this distance, which I'm going to call roughly, let's say 10 meters. And this distance, which I'm going to say is 15 meters. And let's say this distance right here is 425 meters, something like that. So the total distance traveled would be 425 plus 15, that'd be 440, plus 10, that'd be 450. That should have been bigger than this. Let's do this. Let's call this 475. So I'm going to change that 425 to 475. So I went from 425, so at 50 up. So it's going to be exactly 500 meters. This is kind of weird. I don't really want to do that. Let's actually change that number again. Scratch that 475, everybody. Let's say this distance was let's say it's 520 meters. Okay, I'm just trying to make it a physically reasonable result. So sorry about that. So 520 plus 15 would be 535, plus 10 would be 545. So that's 545 meters. Divided by 600 seconds. And that gives me 0.908 meters per second. So the average speed would be 0.908 meters per second, but the average velocity would be 0.833 meters per second in the direction of 30 degrees east of south. So that literally means if you look due south, okay, like this, and then you say, okay, I'm going to turn east of that, which east is when you're looking to the south, east is on your left. So you turn it 30 degrees this way. That's the direction that it's pointing. Okay. So any questions on that? That's sort of just trying to give you physical examples for the words I was saying earlier. And I just want to make sure that's clear. We've now got some basic formulas in mind. And for instance, to top this off, the instantaneous velocity equals the limit as delta t approaches 0 of delta x over delta t. The good news is we're doing one-dimensional motion. So if you want to talk about a vector, the velocity of the girl, let's say it was 10 meters per second, or actually it was 10 miles per hour. Let's say 10 miles per hour. For me, the velocity of the girl was negative 10 miles per hour because I was just looking in one dimension and the direction is either positive or negative. So when you put the sign on it, you can actually use that as a direction when you're talking about one-dimensional motion. So in my reference frame, her velocity was constant, and it was a constant negative 10 miles per hour. In my neighbors, it was a constant, and it was a constant positive 10 miles per hour. And then in the car's frame, it was a positive, because the car and the non-moving frame that it's referencing should have some agreement on which is the positive direction, or you got to do some weird stuff. So if the car was referencing the same thing as the neighbor, then both of them agree that that direction is positive. So the car would say the girl's velocity is positive 5 miles per hour. Okay, all of that's one-dimensional motion, and that's the way you deal with the direction part of a vector in one dimension. It's positive if it's one direction, and it's negative the other, and that handles it. All right. So now back to those reference frames. So we had a couple examples. We had one reference frame, which was me. Which said, this is my X direction, and probably said my vertical was this direction. And then we had my neighbors, who's just crazy because he's looking from the other side of the road, and his coordinate system looks like this. And he called this his X, which I'm going to call X prime, and this would be his Y. And in fact, I could lay them right on top of each other, because if he's right across the street from me, our origins, at least in the X direction, line up. So putting these two together, it would look something like this. Okay, that's what our coordinate systems look like. You can make an easy adjustment to that. You just say X is equal to negative X prime, Y is equal to Y prime. Because they're identical, the origins are the same and everything like that. That's an easy transformation. And in fact, there's neat ways you could do it with mathematics. And ultimately, what you'll learn later in life is that you do it with a matrix, and the matrix isn't really a matrix. The matrix is actually a tensor, blah, 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 blah. So I just, it's not that hard. Now, here's the other part. What about, let's say, my neighbor and the car? So what happens with the neighbor in the car is, oops, my neighbor is this one. That's their X prime coordinate system. And that's their Y prime. Now, the guy in the car is the same thing, but he's further down the road. So his origin is, off in the in my neighbor's negative X direction. So his coordinate system is going to look like this. So this is X double prime, and this is Y double prime. Okay. So that's what that coordinate looks like. So this is the car, driver, and this is the neighbor. Now, what we could do is we could say, just do the coordinates like I did before. But the problem is this coordinate system, at least according to our neighbor, this coordinate system is moving at 5 miles per hour. Okay. That means the velocity of, let's call this, instead of using the primes, let's call this coordinate system right here was B for Billy. This coordinate system right here was N for neighbor. And this was also N. And this coordinate system right here is D for driver. So the velocity of D as seen by the neighbor is actually positive 5 miles per hour. Okay, notice the subscripts. The first subscript is what you're talking about, and the second subscript is what it's relative to. I could also say that the velocity of the bike, oh, I shouldn't do that. Let's say the velocity of the kid. Velocity of the, dang it, why does it keep doing that? Velocity of the kid with respect to Earth is also positive 5 miles per hour if I happen to be using the same coordinate system on Earth as my neighbor did, meaning the direction they were going is a positive. So you can do stuff like that. Now, how do you actually do this? Well, you can see that there was some initial distance between the two. This is how far, for instance, the car was from lining up with where my neighbor was sitting. And initially, this distance was, let's say, 200. No, since we're doing miles per hour, I'm going to say 0.25 miles. Okay. And that's at t equals 0, meaning when we started looking, the girl was lined up with me, the girl was lined up with a neighbor, and the girl was a quarter mile in front of the driver. Does that make sense to everyone? From this diagram? So you could say basically that at this instant in time, I'm going to write this in blue. X double prime is equal to X prime plus 0.25 miles. You see that's actually how the coordinate works? If you want to, you could say, okay, let's say this right here is a point that they're curious about. Maybe it happens to be a mailbox or something like that. Then this distance right here from their origin to that thing is just X prime. So you can see X prime is the coordinate according to the neighbor. And if you add 0.25 miles to that, then you get the coordinate of the driver. Does that now make sense to you? That this is the way you transform X prime coordinate in the X double prime? Okay, so that's very straightforward. Now that's only true at that instant in time, because if you wait 1 second later, the car is going to have moved. So that's just at t equals 0. If you waited, let's say you waited 1 hour. So in 1 hour, then X double prime would have moved a big distance away. In fact, X double prime would have moved at, since it's moving at 5 miles per hour, it would have moved 5 miles. So it would actually be 4.75 miles ahead of that. So it'd be equal to X prime plus, let's see, oh, minus, excuse me. So that shows you that, in fact, this is a two frames relative to each other that are changing as a function of time. And that's just because the actual frame is moving. Okay. The good news is until we do with relativity, we don't have to deal with the individual x coordinates, but we do have to deal with the velocities. Like, it's very important for me to be able to give you a velocity of the girl on the bike with respect to the house, or respect to the road, or with respect to me, or respect to my neighbor, and then ask you what the velocity of the girl relative to the car driver is. That's a reasonable thing. So what I'm showing you is this coordinate system is going to be changing over time in terms of its relationship between x prime and x double prime, as we can see there. But what is the velocity going to do? Because there is something called the relative velocity. So here's a neat little rule that we can use, and I'll show you a problem or something, and then we probably will only touch it in the simplest of cases. Okay, so here it is. If you wish to know the velocity of object A as seen by object C, oops. So there's the wording I'm using. The velocity of object A according to reference frame or observer C. Okay. It turns out you can actually do that quite well. Sorry about that. You can actually do that quite well by using this formula, and it always works both when we start talking about vectors as well as when we're doing things in one dimension. But it is this: it's the velocity of A as seen by C is equal to the velocity of A as seen by anything other than C. You can literally put any second exponent. The main thing is you want this, or excuse me, subscript. You want this subscript to match this subscript. The next part, I'm going to put B, just because I skipped a B on purpose so I could use it, right? And then I will say plus the velocity of, now here's the key point, the inner subscripts have to match. So that forces me to put a B here. And then the outer subscripts have to match as well. So the outer subscript has to match the last subscript. So I'm going to put a C here.
Hey,
And
Professor, what was the, it says according to what? I'm having trouble reading the handwriting.
That's reference frame
Reference frame, okay.
/ observer. So either one, it could be an actual coordinate system like I showed you, or it could be a person.
Okay, thank you.
Or a planet or whatever. Okay. All right, so that makes sense, right? So you see, this formula will always work, even when we get into 2-dimensional and 3-dimensional stuff. It'll always work. What you're going to do is, in 1 dimension, you're just going to say, you know, hey, the right is positive and the left is negative. So if something's moving to the right, if object A is moving to the right, then VAB is going to have a positive coordinate system. The key to this thing is, I'll write it other than cursive so it comes out neater. All observers should agree on positive directions. In other words, I can't use my frame and my neighbor's frame because I said X was to the right and he said X was to the left. Okay. As long as you use that, you can use any coordinate system you want, no matter what velocity it's moving with. Okay. So let's do an example. I'm going to imagine planet Earth here. And I'm going to say there's a spaceship here. Moving at a velocity of, let's say, 3/4 c. Okay, and I'm going to agree that the right is the positive direction. I'm going to say that's the velocity of A with respect to Earth, because this little vehicle is vehicle A. There's also a spaceship over here that's labeled B, and its velocity is negative, let's say 7/8 c is equal to the velocity of B as seen by Earth. And technically, I can put arrows on them because I have the actual signs on them, so they are quote unquote vector quantities. So this is our example. Let me write example here. Actually, let me start off with black and just separate it from this. Okay. So what is the velocity of A as seen by B? In other words, I see that 3/4 speed of light is how fast the A is going to the right, and the B is going to the left at 7/8. That's like 50 miles per hour and 75 miles per hour headed towards each other. If they got in a collision, that'd be basically the equivalent of a 125 mile per hour car running into a immovable object, right? That's just the kind of math we do. So this should give us something like that, like 125. So let's use our formula. So solution, velocity of A as seen by B is equal to the velocity of A as seen by Earth plus the velocity of the Earth as seen by B. Okay, so there's another rule that goes along with this formula that I gave you, and it should be pretty reasonable. If I say you are moving to the right, which is my positive direction at 5 miles per hour, in your coordinate system, you say to the right is also positive, and you'd see me, of course, moving by you in the left. So what would your velocity, what would you say my velocity was with respect to you? Would it have the same magnitude? Would both you and I agree that I said you were moving at 5 miles per hour and you said I was moving at 5 miles per hour? Yeah, that part's true. Okay. The other part that's true is that, in fact, him moving to the right and agreeing that what I call to the right is a positive direction means he's going to see me go by to his left, and therefore he's going to say I'm going in the opposite direction. So the extra rule that we need is that the velocity of I with respect to J is equal to the negative of the velocity of J with respect to I. So I'm just trying to use two arbitrary letters there, so you know that if you reverse the indices, you have to change the sign. That's all. Okay. So I know the velocity of A with respect to Earth when I'm trying to calculate VAB, right? I know VAE, but I do not know VEB. But using that extra little formula I just gave you, I can say that this is the same thing as VAE minus VBE. So I can quickly get the answer that is 3/4 C minus negative 7/8 C. Of course, 3/4 is the same thing as 6/8, and 6/8 minus a minus is plus 7/8. 6 plus 7 is 13, so that's 13/8 the speed of light, which of course is 1 and 5/8 the speed of light, are basically 1.675, or excuse me, 5/8 is 4/8 is 0.5 and it's 0.625, excuse me. So 1.625 C. And notice it came out positive because B agrees that the direction behind it is the positive direction. Now that's cool. That's actually a result. And it's just like the 50 plus the 120 or 50 plus 75 gave us 125. So that's the actual answer. Now, the neat thing is, and I'm going to do this little example part just for fun, because later we are going to cover relativity, but it turns out this answer is actually right with respect to relativity if you just make one correction. And I'm going to do it now. The velocity of A as seen by C relativistically, and this is all one dimensional. It gets nasty with multiple dimensions, so I'm not putting vectors on here, okay? As long as you use the vectorness in one dimension, it'll work out fine. But it's exactly the same formula. The velocity of A as seen by B. That's terrible. I hate my writing. Velocity of A as seen by B plus the velocity of B as seen by C. But it has this part. And that C is the speed of light, not to be confused with frame C. Okay, so in this case, if this was relativistic, which is really what has to be done when you're talking about speeds comparable to the speed of light, VAB would actually equal 3/4 C minus negative 7. Whoa. 8C over 1, and we now have a minus there, so it would be 3/4 C negative 7/8 over C squared. And you can see what happens is this C squared cancels out with those two C's, which is nice. And that still gives us on top 13/8 C. But check out what happens to the bottom. I do 3/4 times 7/8. That'd be 21/32. So this is 1. Notice the minus and minus makes a plus. 1 plus 21/32. 1 is 32/32. So 32 plus 21 is 53, I think. So we're going to do 13/8 times C over. Now, again, this is 32/32. So 32 plus 21 would be 53/32. And what you'd get is you're actually going to multiply 32/53 times 13/8. And you see that the 8 cancels out with the 32, leaving just a 4. And 4 times 13 is 40, plus 12 would be 52. So we end up getting 52/53 C, just barely under the speed of light. Ain't that cool? So you won't have to do this till we get to chapter 31, which is what we do after chapter, I think, 11. But anyways, that's just a neat little sidebar. You can see the formula only changes a little bit, but notice how it just perfectly makes the velocity come out just under C. It's literally always, I mean, every time I've worked this, I either get C because one of them happened to be moving at speed of light, or I get literally a numerator that's one smaller than the denominator multiplied by C. So any questions on that? Don't worry, you're not going to be asked to do the relativity ones, not in this chapter. But what we're doing here, this blue part where I solved this, that is called Galilean relativity. So that's something we're definitely going to do. All right. Any questions on that? All right, so we got about 13 minutes left. I've got to now take you out of the relative velocity area. And again, I'm going to talk about motion. So Galileo, once he was sentenced to in-house arrest after the Inquisition, where they showed him the instruments they'd used to cut out his entrails through his gonads, he wisely chose to take the brave route and say, I'm going to live a little longer by doing whatever the heck you tell me to do. And he went in to his home, and he was under house arrest for the remainder of his life. He was pretty old anyways. He was going kind of blind, so it didn't matter too much. But he was forbidden from the study of astronomy. But he had already made, unique discoveries. Like he showed that there were 4 what he called Medicean moons. We now call them the Galilean moons. But there were 4 Medicean moons that orbited Jupiter. No one in any model had Jupiter sitting still. So there was clearly a case where planets were following and not being left behind, where moons were following a planet, not being left behind, which was one of the arguments against the heliocentric model, is that if a bird was sitting in a tree and the Earth was orbiting the sun, if a bird saw a worm on the ground and just like jumped off the limb, the Earth moving so fast in orbit around the sun would leave the bird behind. They didn't understand Galileo's law of inertia, which ultimately became Newton's first law of motion. So they didn't understand that, but that was the moons of Jupiter, the Medicean moons, or what we now call the Galilean moons, Io, Europa, Ganymede, and Callisto. They were actually proof positive that something in the universe is not getting left behind. So that was pretty good. Plus, he saw that Venus had all its phases, which couldn't work with the Ptolemaic model, and so on and so forth. So he just ran with it, but he wasn't allowed to study that anymore. But he figured out, hey, I need to understand motion a little better, because clearly Jupiter and its moons are doing something crazy. So he went in and studied balls rolling down inclines. He did inclines because he realized when he dropped the ball, it would go so fast that he couldn't tell whether it was going instantly fast and going the same speed all the way down, or if it was speeding up or what. And in fact, we didn't really have good words for speed and velocity and acceleration and all that stuff back then. So what he noticed was when he rolled a block down an incline, or rolled a ball down an incline like such, and he, of course, time was a problem back then. We didn't have really good clocks, especially not for measuring things like tenths of a second. But he made one that worked pretty well, and it was a water clock. So basically, if you wanted to start timing something, you have a container down below a valve with water in a tank, and you take and measure that container to catch the water, and you know what that mass is. And then you open the valve and water starts to fill it up at the same time you start the motion. And then when the motion's over, you close the valve and then you weigh the water. And if it took twice as long as the previous measurement, then that water should weigh twice as much. So that was his clock. What he discovered is that in a given interval, when an object was allowed to roll down an incline, it would go one distance in the first instant, and then a bigger distance in the second instant, and then a bigger distance still in the third instant. So objects speed up when falling. That's a big deal because you can't see that just looking at vertical motion. So his idea was to make a small angle and look at that, because trigonometrically, the vertical acceleration can be gotten using trig to get back the vertical acceleration by just using the angled acceleration, if you will. He also noticed that balls, when they encountered inclines, in that case, for a given interval, they would go a good distance, and then the same interval later, a smaller distance, and the same interval later, a smaller distance. So objects slow down when rising. So he argued that if it's perfectly level, then he expected it to be moving at a uniform speed and stuff like that. But the main thing is he's now seeing that, hey, in a given interval, say a tenth of a second, or let's say a 3 grams of water. Okay. In the 3 gram of water time period, the ball went, at least in this first case, might have went a distance of, let's say, 5 centimeters. But in the next one, it went 8 centimeters. And then in the next one, it went 13 centimeters. So he said uniform motion, he sort of defined a quantity called uniform motion, would be constant speed. So means for a given time interval, like 0.1 seconds. The object will travel the same distance. So that gave us essentially a velocity sort of speed scenario where you could define the speed as a distance divided by time, and uniform motion would be a constant speed. And a constant speed means it's always going to travel the same distance in any 0.1 interval. So if you lock down the delta t in the s equals delta t, s equals d over delta t, if you lock down the delta t and you lock down the d, then you see, oh, that makes a constant speed. So obviously a natural definition of speed would be distance divided by time. And he went further and realized, hey, the velocity actually changes by a unique amount as well. And uniform acceleration was defined which is constant acceleration. Now, before I go into this part, I want to ask you guys, do you know of a nice, almost experimental result sounding data that a car dealership will give you when they want to tell you this car is really good at accelerating? It has a lot of acceleration. Does anybody know that? I'll give you a hint. It's got the word 60 in it.
You mean like a 0 to 60 acceleration?
Exactly. Yeah, 0 to 60 in 4 seconds is actually pretty good. That's like a, that's like a Mustang or a Camaro or something like that. In fact, the newer ones might even be getting less than 4 seconds. But that used to be a really good one. But I like the number 4 because it goes into 60 really evenly. So as our archetypal example for acceleration, acceleration could be going from 0 miles per hour to 60 miles per hour in 4 seconds. So you can see there's a change in speed, and there's a change in time. And in fact, it's natural to think that the velocity change divided by the time taken would be a measure of acceleration. And that's ultimately what we do, is we say the acceleration is the change in velocity divided by the change in time. That's the average one. So constant acceleration means for a given time interval, the object will change speed. Whoops. I'll say velocity, but speed also works. So acceleration is delta V over delta T. And that's, of course, average acceleration, just like this was just average speed. Okay. So a typical acceleration might be 2.0 meters per second every second. That means every moment that this thing moves, if you look from one time period to 1 second later, the velocity is going to increase by 2 meters per second. So if I made a table of times in seconds versus velocities in meters per second, 0, 1, 2, 3, 4, 5, and V0 was 0, then the velocity at 0 would be 0. But 1 second later, it'd be 2. And 2 seconds later, it'd be 4. And 2 seconds later, it'd be 6. And 4 seconds later, it'd be 8. And 5 seconds later, it'd be 10. That's what uniform velocity or uniform acceleration means. And that's what that's what Galileo discovered about these balls going up and down the inclined plane. He discovered that the acceleration due to gravity, once you corrected for the angle of the incline, he discovered that the acceleration due to gravity, G, was equal to 9.80 meters per second every second. And that's it mathematically exactly the same as meters per second squared, and that's what your book writes. But I really think you should take the time to write it this way, or at least as a bare minimum to say it this way. So do not say 9.80 meters per second squared, even though that's really easy. Say 9.8 meters per second every second. So you get the idea that, hey, if I drop a ball and there's no air resistance, let's say from a really tall building like that one in Dubai, for instance, if I drop a ball after it's traveled 1 second, I know its velocity is going to be 9.8 meters per second, which, by the way, is about 32 feet per second. So the acceleration is 32 feet per second. I know at the end of 1 second, that ball will be traveling 9.8. I know at the end of 2 seconds, it'll be traveling at 19.6. And I know at the end of 3 seconds, it'll be traveling at 27.4, and so on and so forth. So that's the advantage of using saying the units of acceleration as meters per second every second. Okay. And what Galileo discovered was that all objects fall at the same rate, independent of the motion, independent of the mass. And, you've probably heard the Eiffel Tower, the Leaning Tower of Pisa story and stuff like that. We now are pretty sure that didn't happen, specifically because they had a lot of red tape in Italy at the time, and there would have been all sorts of paperwork for someone to get into the Leaning Tower of Pisa to do that. But still, the experiment holds as reality. So I will next time go over the actual equations from kinematics and derive them. But in the meantime, I'd highly recommend you go into my YouTube channel and look for my derivations of the actual kinematic equations. So you'll know what I'm doing. You'll be able to better understand what the book is doing. So next time, make sure you've finished reading chapter 2 before coming to class. And you should be able to start on chapter 2 homeworks. I didn't mention this earlier, I meant to, but I am moving to chapter 1 homeworks. For those of you who didn't do it, you still have a chance to do it for full credit. I want to move the homeworks back to be due this coming Sunday. And those of you who already did it, no matter if your grade was bad or not, I'm going to give you an extra homework assignment of 100. Okay. So you folks are free to go. I'll wait for the last person to leave, and then I'll close this off. So I have a question here. What homework is due for this week? So if you look in your module 1, That's what was due supposedly by midnight on Sunday. But module 2 does the same thing for this week. The only thing that's not showing right now is those 2 introductory assignments, Introduction to MyLab and Mastering, and Physics Primer. So Physics Primer, Introduction to MyLab and Mastering, chapters 1 and chapter 2, homework and conceptual questions are all due this coming Sunday. You should have already done chapters 1 already. And the other 2, the introduction and the primer, are extra credit, but you should definitely do the MyLab and Mastering so you'll understand it.
Professor, what homework is due tonight? Isn't there
nothing? Even if I've got it set for tonight, right now it's gonna change. Everything's gonna change and be due on Sunday, which I think this coming Sunday is the 22nd. Yes, 22nd. So the 22nd at 11:59 p.m. Chapter 1 homework, chapter 1 conceptual, MyLab and Introduction to MyLab and Mastering, Physics Primer, chapter 2 homework, and chapter 2 conceptual. That's all due at 11:59 on Sunday. Did you get that, Lee?
Sorry, I did. Thank you.
No problem. Anybody else have any questions? This document will be posted on my Google Docs probably within 10 minutes. And this video will be posted on MyLab and Mastering this afternoon sometime, if not this evening. I tried to erase one of them. You only need to do one. Hopefully you won't find the links to the other. I don't know why it has 2 in there to start with, but hopefully you won't find the other ones. I'm going to go ahead. If you haven't, if you've already done one, if you haven't done one yet, don't start. I'm going to try to go into MyLab and Mastering and erase one of them if you see them on that side. But I think all you should see them is my side, in which meaning on Canvas. If that's the case, then it's already taken care of. Okay. Anybody else? Danielle, George?
I have a question about the extra credit, so I'm just waiting for
Danielle, sorry.
You can call me Danny. So Angie and Clinton and I have been working on the extra credit, and we finished it, but we're just confused about the answers that we got.
Mm-hmm.
So do you want us to actually find like a numerical value, or is it all supposed to be?
You should find a numerical relationship between R and H. That's the extra credit you're talking about, right? The unit
right.
of maths. Okay. Yeah, you should find a mathematical relationship between R and H.
So we did do that.
Okay.
In part A, we got R equals H over 2. And then for B, we got negative H equals R. And that's, Angie and I were working on it last night. We got stumped.
Okay. So the part 2, you're not doing anything with that far as trying to solve for anything. So what you do is you first take the surface area formula, which has R's and H's in it, and you take the volume and density formula, which has a volume and an H in it. We're going to have to hold the V constant. So what you do is you solve for H in the volume formula and replace that H in the surface area formula with that. So what happens is your surface area formula, instead of having R and H for it now, it just has an R and an H in it. Excuse me, an R and a V in it, not an R and an H. And the H is definitive, or excuse me, the V is definitively constant. So you take the derivative of that, set it equal to 0, and you'll get R is related to volume some way. Now you plug back in that volume formula that you used before so that you can get rid of the V and have just R and H. And like you said, you should come up with something like R equals H over 2 or R equals 2H or something like that. That's what happens when you set the derivative equal to 0 to find the extrema.
Yes.
The second part is now you take that same function, the surface area, with just the R in it. In other words, with just the R and the V in it, and you take the second derivative and just see if that is positive or negative, because if it's negative, then you know it's a maxima. If it's positive, then you know it's a minimum.
Okay, so I guess like we got mixed up on the way it was worded, because it sounded like you wanted us to find the minimum. and we didn't know, or if we didn't know if you wanted us to verify if it had a maximum or a minimum. So
Yeah, so the first part, when you did set the derivative equal to 0, that is finding the extrema. And
yes.
if it only offers one thing, it's either going to be a maxima, a minima, or a point of reflection. The
Correct.
second part, when you take the second derivative, just showing that r equals h over 2 or whatever, just showing that the second derivative of the surface area is positive is really the way you show that that was a minima.
Okay, so I guess like this doesn't prove that it has a minimum because I don't know. I'm sorry. I'm
Well,
just kind of confused.
I get it. You shouldn't have an equation on that second part. You should just have second derivative of surface area equals blah, and it should be some number that clearly cannot be negative.
Oh, okay.
And that's you're done at that point.
Okay, so I guess that's all I have for it. So thank
Yeah,
you.
I'll check it out. And if it's wrong, I will make a comment about what's wrong with it and give you time to fix it, and you'll still get the 100. So you're golden.
Okay. Thank you.
No problem.
Thank you, Professor. Hope you feel better.
You're welcome. Thank you.
Thank you.
Thank you, everybody, for coming. Anybody else have any questions?
Hey, Professor. I
This is John. Yeah, I was just looking at your message. Yeah,
What was that?
absolutely. You want to attend tonight? Or are you
is it
wait
the
till
same
next time?
lesson?
Yeah, it's the same lesson for tonight. So yeah, you can attend tomorrow. You can attend on Monday night if you'd like.
Okay, is it the same Zoom link as this one?
No, I'll send you personally a Zoom link. Did you ever send me a text message? I think you did, didn't you?
Yes, I did.
Okay, I'll send it through that.
Okay, awesome. And then do I just upload the stuff like labs and all that stuff just onto Canvas on the same?
Yeah, on this course. If I manage to get enough students off where I can do it, I'll just switch you one day, but I don't see any need to. I think I can just leave you in this one. It'll be fine.
Yeah, I don't think it should be much of an issue. All
Okay.
right.
Thanks, John.
No problem. Thank you.
You too. No, the way you turn in your extra credit is you click on the extra credit assignment in week 1, and it gives you a document to upload. That photo should be converted to a PDF and then turned in. I think that's Angelina that asked that. Let me stop sharing screen real quick and let me share a different screen. Let me share, Canvas. So if I go back
Yeah, so
here,
I know where to turn it, and I'm just asking because I'm kind of confused on how you're saying we should get a number for the second derivative, because we still have we have v there and we don't have a number for v.
right.
So-
Well, for starters, you're going to get rid of the V and put it back in. So the second derivatives is only in terms of R and H.
Yeah.
Okay.
We
And then
got
you're going to
that.
plug in R equals like 2H or H over 2 or whatever you found. And what you'll see is there's a bunch of squares, maybe some maybe some addition, but there's no subtraction. So it'll be impossible to get a negative number.
Okay, so we're supposed to take the answer we got in the first derivative and plug that into the second derivative.
Yeah, because that's the specific place where it'd have to be positive for it to be a minima.
Gotcha, and then that would leave us with only h, and we would get h equals something.
Yep. Or yeah, exactly. H and R or whatever. Yep.
Gotcha. Okay, no, that right there makes a lot more sense. Thank you.
No problem.
Thank you, Professor. You have a good day.
You're welcome. Thank you.
I did have one more question. What was the reading that we were supposed to do?
Oh, in general, you always want to read the material I'm going to cover before I cover it. So I suggested for best results to make sure you finish reading chapter 2 before we meet again on Monday.
Okay, so finish reading chapter 2. Is there like a place where you post which chapters we're supposed to be reading before the lectures, or?
That's yeah, it's basically in your syllabus where I give that table of what's covered on each week. That's what you're supposed to do. So like the day that I cover chapter 1, you should ideally have at least the first half of chapter 1 read. I might go a little bit further than half, or I might go a little bit less, but you'll be pretty well prepared. You could, in principle, have the whole of chapter 1 read, but if I'm taking 2 days, that's a little more than you need to. So I'm trying to, give you as much heads up as I can. But yeah, it's all on the syllabus according to the calendar.
Gotcha. Okay, that makes sense. Thank you.
No problem.